this Q, it would be the other way around. So if I'm not making a hash of it now, then this would actually be the reduced BDD that comes out. Okay, what is the lesson here? I showed you a construction for one particular example, but I tried to make it clear how the construction works in principle for arbitrary BDDs and for arbitrary operators on those BDDs. If you start with two reduced BDDs, what is the maximal size of the combined BDD? You can at least give an upper bound for the size of the combined BDD.
Well, it's on the sheet, so.
Is it?
At the bottom.
Yes. Okay. Indeed. But can you see why? So it says on the sheet the maximal size is quadratic. Or if I could make it a bit more precise, the maximal size is the product of the sizes of these two starting BDDs. Why is that?
Because it's binary, so
What do you mean by binary?
yeah, if we, I don't know.
Well, I mean, if you see how I labeled the nodes of the constructed BDD, they are all pairs, and maybe that's what you mean by binary. They're all pairs of nodes of one together with node of the other. And there can never be more than number of nodes times number of nodes of those pairs.
If you have distinct propositions.
Sorry?
If you have distinct propositions.
True. In general, it will be better. The upper bound will be better than the complete product of those two sets, because you can, in principle, it's not necessarily there is a limiting factor about the levels. You will never okay. Let's just observe that the absolute upper bound is the product of the sizes of those two BDDs. So that's the worst case. In this case, I had in my combined BDD, I actually reduced it from the start. But if I hadn't, then there would be, I think there would be 8 leaves. So I would have 15 nodes in my unreduced BDD, which of course is smaller than 25, but it's still quite big. In my reduced BDD, I only have 7 left, so the reduction is actually quite strong here. And that's the pattern. So it might be that the combination of BDDs blows up the whole thing, and then hopefully the reduction will shrink it again. But in the worst case, I already told you last week, I mean, the BDDs are no gold, silver bullet. It's not the case that suddenly you have a good representation for all formulas. There are formulas for which there are only large BDDs. And then, of course, the reduction won't bring you anything, and the whole construction really does blow up. Okay, but that's the lesson, and I hope that you see how it works in principle. And then this is the strength of this BDD representation, that in very many practical cases, if you are lucky, or if you are somehow intuitively wise about the ordering of your propositions, then your BDD can stay small. Okay, so that was the tail of last lecture, and there's a bit more tail of last lecture actually, which has to do with sets of.
Yes. I was wondering, like, you're talking a lot about the ordering of the decision tree. What if the order was different?
Yes. Well, this example doesn't show it so much, but I did have an example. I think I just showed it maybe very briefly at last lecture, but here we have an example of a formula with two different orderings, which lead to two quite different looking BDDs. Moreover, one of them has clearly more nodes than the other. And if you see the formula, which says P or Q, P and Q, or R and S, then this ordering tackles P and Q first, so the proposition in one sub-formula first, and then the proposition in the other sub-formula, whereas the other ordering mixes the propositions of those two sub-formulas. Well, that is one of the heuristic rules for a good ordering of, and good means giving rise to a small BDD, for a good ordering of your propositions, you should not mix parts of your formula indiscriminately. But it's a rule of thumb, right? It's a heuristic. And there is no very clear understanding why this works.
But if you would go through the binary decision tree, you would end up with the same results?
Yes.
Okay.
Yes.
I was wondering that because it looks like, because you're mixing them up here, as if like the ordering of your formula operators is going to be different. But maybe that's just the way it looks.
Yeah, so in the BDD you don't see the operators anymore.
No,
right?
exactly.
This is just,
Yeah, exactly.
you lose all structure of your formula.
Yeah.
And then how many nodes you need depends on whether your sub-results already collapse at an early stage. So here you see that actually for every proposition, there's only one node where you need to evaluate that proposition. And that's because the AND and the OR have this property, if you know that one operand is true or false, depending on whether it's an AND or OR, then you can stop. Whereas if you tackle the proposition in a more random order, you can't make use of that property so much, and therefore you sometimes need to evaluate the proposition more than once. That's a bit of the intuition that I have for this stuff, but it's not easy in general. And it is the case that there are formulas that have a very good representation given a right ordering of propositions, so that the BDD grows only linearly in the size of your formula. Whereas if you pick the wrong ordering, it grows exponentially in the size of your formula. So it really can matter. And there are also formulas for which, whichever ordering you pick, they will also always grow exponentially in the size. The BDDs will always grow exponentially in the size of the formula. And the last was to be expected, because if that were not the case, then maybe suddenly we would have a non-exponential algorithm for satisfying things about propositional logic, and we know that well, nobody believes that exists. Okay. So there's one last thing I want to mention, because there's unfortunately not that much time to go into this, but there's this technique called set solving or satisfiability solving. Does the term set solving mean anything to you? Anybody who heard this before? Yes?
2 weeks ago.
Ah, in this lecture, I mentioned it. Okay, I meant in another context. No? I think Peter, you said Nico? Where did you hear this?
ADC.
Ah, okay.
Organization versus complexity. It was discussed about the NP-ASP problem.
Yes.
Could you reduce something to set solving? And they gave some examples of some problems that could be reduced to set solving.
Yes. So set solving, I mean the word set solving just means satisfiability solving, and that is the problem, or that's one version of the problem we've been dealing with all along. I mean, a semantic tableau is a technique for showing a formula to be unsatisfiable or satisfiable. So that is one technique for set solving. But actually people use it for a specific different technique that also gives you that kind of answer. And that technique is actually quite close to resolution. And I'm just going to go through it very, very quickly to impress you. First, I have to say something about complexity again. Why do I have to say this? I hope this still sticks in your mind from a few weeks ago. An algorithm in general is of course deterministic if it has a single computation path for every input, and non-deterministic otherwise. And we say it's polynomial if the running time is bounded by a function that is a polynom in some exponent, so maximal exponent. Whereas if it's only bounded by an exponential function like this, where the nx itself, the size of the problem itself, appears as the exponent, then we call this an exponential algorithm. And we have some deterministic algorithms already for establishing satisfiability. What are the exponential algorithms that we showed? Remember? What did we do in the previous lectures? BDD is one, yes. And, well, we had several actually, right, by now. Deduction systems is, okay, in the reduced form of Gensen, it's actually an algorithm.
Resolution.
Resolution and also the semantic tableau, I would say. And those are exponential algorithms in the worst case. We also have a non-deterministic algorithm for establishing satisfiability. I mean, this is like very, very obvious and stupid kind of answer.
Just
Yeah.
guess
Just-
correctly every time.
Yeah, guess an answer and check it. Guess an answer non-deterministically and then check it. So choose a valuation or interpretation, I should say, such that the formula evaluates true. But this, of course, is magic, but it's very efficient if you can build a machine that does the magic, because establishing that this is actually the case is the only thing that you have to do after applying your magic, and that is only linear in the size of the formula. Okay, so I don't know why I'm repeating this. I think we had all of it. Sorry. Practically efficient set solving. It turns out that in many cases this can be done, and it is it's a variant of the resolution. So in resolution, we essentially only apply this resolution rule to a set of clauses. So you build the clausal form, then you have a set of clauses, and then you apply resolution. But it turns out that